In the name of God. Hi everybody, my name is Mohammad-Sajad Kasaei. I'm from MDS Research Group of University of Islam. Today I present our paper which is defined context of model comparison, and the title of our paper is a rule-based language for configurable n-way model matching. In this presentation, first I talk about the problem of our paper, and then I'll demonstrate the problem with the running example. Then the proposed approach will introduce. After that, I'll demonstrate our case study and implementation of our approach, and finally I'll conclude the paper and mention the future work. Okay, so to build complex software-intensive systems, different stakeholders from diverse domains must collaborate to create and modify models. Model matching is a fundamental precondition of collaborative development, which is concerned with identifying common elements in input models. In this respect, the modeling community has investigated the model matching algorithms. Finding correspondences between model elements is an NP-hard problem. Therefore, researchers have focused on comparing two models at the same time. Comparing two models can be generalized to more than two. However, using these algorithms for comparing multiple versions may introduce incorrect results. Moreover, the comparison may perform suboptimal processing, and the order of comparing input models influences the result. Simultaneously comparing n input models is a solution to cover these issues. There exist only two algorithms that simultaneously compare n input models. The first is n-way merging and the second is Raccoon. These algorithms deliver better results compared to sequential comparison. However, they do not provide a configurable mechanism that determines precise language-specific algorithms for specifying comparison criteria based on user-defined requirements. Therefore, in this paper, we propose a formalism that can help users define comparison criteria for models of diverse meta-models and technologies in a rule-based manner. We introduce an n-way matching algorithm that considers multiple input models and constructs a chain filled through all matching correspondences. To illustrate the motivation of n-way model matching, we provide a simple running example using three different fragments. In this example, white nodes represent the elements that have counterpart similar elements in the other input fragments. In contrast, black nodes represent the elements that do not correspond to parts of other input fragments. We aim to compare three different fragments are shown in the figure on the left and create match lists that consist of similar elements. In the figure on the right, we indicate the final match list for our motivation example. As you can see, for example, the A nodes are specified as similar in the three different fragments. The proposed formalism. We determine a set of rules that help users to specify precise model comparison criteria. Comparison rules are defined by Rule 1 to Rule 14 to characterize formal terms and conditions. Rule 1 demonstrates our n-way matching module, which consists of 4 different parts. First, we should use module keyword, and after that, the name of the module comes. Inside each module, we should determine the definition of meta-models, homocom rules, which refers to homogeneous models, and heterocom rules, which refers to heterogeneous models. Okay, so Rule 2 shows how we can define our input meta-models. For defining input meta-models, we should use import keyword, meta-model name, which is a string, column symbol, and finally the address of input metamodels comes. Rule 3 and 4 demonstrate how we can define our metamodel name and the address of input metamodels. Rule 5 shows homocom rule. For writing and defining homocom rule, we should use rule keyword. After that, the name of rule comes. In the following, we should write match homo keyword, and then metamodel definition comes. If this rule extends other rule, we can add this situation by using extends keyword. In the following, we should write compare models keyword, and after that column symbol, and then we should write homo statement. The homo statement determines the comparison criteria. Okay, so rule 6 to 12 show the detailed explanation of defining homocom rules. And rule 13 shows how we can write and determine heterocom rule for heterogeneous models. Each heterocom rule consists of rule keyword, rule name, which is a string, match heter keyword, metamodel definition, which refers to the element type of the input metamodels, with keyword, metamodel definition. If this rule extends other rules, we can use extend keyword. And finally, we should use compare models keyword, column symbol, and heter statement, which determines comparison criteria. For example, user wants to compare models and elements based on the name. User can add this in the heter statement. The last one is rule 14, which determines how we can write a heter statement. It's similar as homo statement. Now look at this simple example in which we write two different homocom rules for a state diagram. In this example, we specify a name for our module, and then we use a UML metamodel, and after that we write two different rules. One of them is for state and the other is for transition. Okay, so for executing the semantic of our rules, we introduce an n-way model matching algorithm to calculate commonalities and differences between multiple models. The worst case runtime complexity of our algorithm is order n m2, which shows an improvement compared to other n-way algorithm. We demonstrate how our approach can compare input models by indicating running example at the high level of abstraction. We assume that the nodes are compared based on their names. Therefore, two categories of elements can be identified: similar and dissimilar elements, shown by white and black colors. Moreover, some similar elements may not conform to each other based on model structure. For example, consider a situation where two elements are identified as similar based on common names, but one of them is concrete whereas the other is abstract. The execution of our algorithm delivers mismatching conformance for these elements and considers them dissimilar. These nodes are graphically shown in figure on the left by the gray nodes with dot lines. The formalism narrows the comparison search area. This reduces the number of comparing operations. Therefore, our algorithm only attends to the elements that belong to the formalism, and the elements that are not in the domain of the comparison are ignored. This schematically demonstrates in the figure on the right. Now look at the workflow of our algorithm. The algorithm needs to iterate over all input models. In this example, 3 iterations are performed. In the first iteration, elements of the first input model separately are placed into a group. In the second iteration, the n-way matching algorithm compares the elements of the second model and locates them in the appropriate groups. The algorithm automatically creates a new group if such a group cannot be found in a chain. Finally, the algorithm compares the last model elements to produce the desired results by running the third iteration. And we evaluate the applicability of the proposed formalism via a descriptive case study. We consider an ATM system that provides banking services for the users. This figure illustrates the original version of the UML state machine as well as the 3 derived versions created by 3 modelers. The original version consists of 2 states named idle and working and 2 transitions named card in and done. The modifications of each modeler are indicated in red, blue, and green colors. The specification of matching rules for state and transition elements are mentioned using the proposed formalism. We also have implemented a syntax error editor and a parser using Xtext for our formalism in the Eclipse framework. The features of our editor are keyword highlighting, error awareness, and smart terms compilation. And in the end, I conclude the article. We propose a formalism for specifying the comparison rules for models of diverse meta-models. We also implemented tool support, syntax error editor, and parser that allows user to write comparison rules for any EMF-based models. And moreover, we proposed a matching algorithm for extracting commonalities and differences from multiple models. As a feature work, we aim to extend our formalism to define the n-way comparing language for multiple input models built upon a well-known modeling framework such as Epsilon. The complementary work is required to implement the execution semantic of formalism and algorithm by introducing an n-way matching engine. Furthermore, we intend to conduct a systematic comparative analysis to investigate the comparison of the homogeneous and heterogeneous models. Thank you for your attention. If you have a question, I'm ready to answer your questions.